All right. First, want to thank Discoveries for asking me to speak today, and thank you all for being here. Don't have the presentation up yet, but let's see. You guys have it? All right. Now we're rolling. Okay, so we're going to talk about oriented core workflow, the workflow that we've developed for our company, OTS. The goal is to maximize value from the core drilling investment. So a little bit about our company. We started this company in 2016, and we've been working with oriented core for over 10 years, taking a lot of the ideas that have been developed in Australia and in North America a little bit. We've worked with over 120 companies globally to establish a workflow for structural data with oriented core drilling. We've collaborated with several drill companies and IMDEX, and we're actually learning every time we go on a new project and just taking all the good ideas that we come across all over the world to glom into a workflow that's effective. So why orient core? We need to recover more data, more value from the core drilling investment, and really the goal is to build a better geologic map with the core hole. It's kind of like if you have a surface mapping program or your underground mapping and you don't have your geologist collecting structural data. And we don't understand why sometimes core is being drilled when structural data is not being measured in the rocks directly. And so there's a lot of implications for geological engineering and vectoring towards mineralization. There's times we'll work with clients and they're in greenfields terrains and they'll say things like, we're not ready to do this yet, we're not ready to collect structural data in our core, and our argument is you need to know the most when you know the least. And so basically it's a cost-effective solution, because if you're drilling 3 core holes that are used to define a planar feature, you know, like a fault zone or a vein zone, if you can get those vectors with 1 core hole, you're already saving money. And so really, we need to go backwards here. Yeah, stay on that slide. So really, a single hole can provide very valuable insight. And so I think as geologists, most of you understand that geological structures control things that we care about, like geophysical anomalies, geochemical anomalies, alteration, things like that. And really what we're trying to do is get the ability to model permeability controls that were existing at the time of the hydrothermal event. And so if we have an opportunity to model that, that's going to really help us with exploration. So the advantages of oriented core, there's a few different ways to get structural data out of rocks. But we like oriented core because the tools fit in a briefcase, and basically the user controls the process. We want geologists to behave like surface mappers with core and in the core shack. And so if the geologist is able to make a meaningful data set and make choices on what they're going to measure in the rocks, just like they were mapping on the surface, that's when we get the best data sets to work with. And so since they control that process, they have the ability to make a direct link between structure and all the things that it controls, like the rest of the logging, like lithology, alteration, things like that. And there's a lot of value in that part of the workflow. And also, you get a chance with oriented core to get structural data with every run of core that's being drilled. And there's very limited downtime. The tools are designed to keep drilling going and to keep the next tube going down right after you pulled up the one that was just drilled. And so that's the way that those things are designed. It's very efficient. So we've noticed some problems in the industry where people have tried to do this before. They either didn't trust the data that they were generating, or they didn't know what to do with the data that they were generating. So we attack those 2 problems right off the bat when we get involved in a project and train. We want geologists to be able to trust their data, so we end up logging a quality assurance, quality control QC for the data. It's an orientation log. And then we guide geologists into the process of, okay, what are we going to do with this? How are we going to join this data with geochemistry, alteration, things like that, and be able to rapidly query that data set and be able to interrogate that data set and actually get to accurate 3D modeling, which is really what we're after here. So there's a few elements that are available now in the industry. There's quite a bit of software and hardware that's been developed recently that's very cool. We like to work with the index system because it really gives us a chance to have an entire ecosystem that's got, you know, our core orientation tools basically up here in the circle, our structural logging tools, and then data management tools like the Index Hub, which then can leak to analysis tools like IOGAS, and then really the end result is getting structural data into 3D. And so really one of the reasons I show this slide is because what's important here is we want to have some quality control process that's really at the stage of core orientation and structural logging, because if we don't have quality control, then we end up, go back to that back slide, if we, go back. If we don't have quality control, then we end up loading garbage data into all this powerful software solutions that we have in the industry. So we want to make sure that we're putting good data into these software platforms because that'll maximize their utility. So I want you to understand a little bit what is going on with core orientation tools. And so up here we have the Reflex ACT tool. It's got two parts. It's got a controller and a downhole tool. These tools have accelerometer sensors in them, which basically just measure the acceleration vector of gravity. And so that tool that is screwed on to the top of the core tube that's going downhole, it's taking a gravity measurement once a minute. And so it's the same kind of sensor that's in your smartphone. Whenever you turn the screen on your smartphone, it basically is going to orient the screen relative to the viewer. And so that is screwed on the top of the core tube. And what's happening is when core orientation is going on, it's actually the tube steel that the rock goes into that's being oriented. And what controls the relationship of the rock to the steel is the lifter spring. And that goes and slides behind the barrel or behind the drill bit in the barrel. And what we need is for people to understand that that rock, once you drill around a core, that rock at the bottom needs to be attached to the earth, and then when the driller pulls back, they snap it. And that's how the process works. And we basically go in and train that, because if people don't understand how that works, then they don't make good data. So we have a quality control process for the rest of the data. If we drill around a core, you can see there's an orientation mark at the downhole end of the run and a line drawn up lock core. And basically what we're doing is we're trying to get this mark to test with the mark for the run that was previously drilled. Okay, and so there's a probability statistics as part of our quality control system where basically you have a very low probability of a mark from one run randomly meeting the mark from the run that was previously drilled. So that's a 100, it can be calculated, it's 1 in 360 degrees. It's like a 0.2% probability. You're going to go back, you guys. Back. So it's a very small probability you're going to get these two tests to match up to each other. Every time you drill a new run of core, it's a new test from the quality perspective. And so what we do is we measure these lock angles between runs. And if we get a good lock angle that's very small, we'll measure it with the wraparound protractor. That means this mark is good, this line is good, and that mark is good. And so basically we just create attributes to connect to the structural data so we can then filter and keep bad data from getting into 3D models. Go to the next slide. Oh, go back. So when we get on site and train, we just, you know, it doesn't take much time to do this training. It's just like any kind of workflow that we do. You know, it's, if we do some proper training at the beginning of a drill program, then we're going to get a lot better data. And the data is very powerful. So what we do is we train geologists on what they're measuring. Like no matter if they're using the IQ logger, which is a laser-based structural measurement tool, no matter if they're using that or manual measurements, we want them to understand that, you know, when you have a planar feature in core, The alpha angle is the angle to the core axis, and the beta angle is what's related to the orientation line. And the orientation line is the direction of gravity in the hole. So we're relating these planes to the gravity direction. And what we like about oriented core is we have the ability to have this reference line on all the core that comes into the core shack, which is showing us the gravity direction. And it helps inform the rest of the logging process, because then geologists can see the patterns. You can see there's an epithermal vein here, and then basically we get into some tufts, epithermal vein, a fault, and then very organized sheeted veins down below that fault. And if the core is just turned randomly in the core boxes, it's really hard to see that kind of organization in this system. And so having a reference line from core orientation really allows you to inform the lithology logging, the alteration logging, things like that. And so that's one thing that we like about it too, but we want to make sure that that line is in the right place. So as far as data is concerned, we're looking at, when you're measuring a structure in core, it's at a very specific depth in the core hole. So what we want is a little bit of metadata that's connected to that, and this is point structural data since it's occurring at a specific depth. So if we've got, veins, we want to know what's in them. We want to know how big they are, and scale. There's this metadata that's going to be used for querying later on. And really the beauty of this point structural data is that we can join it with interval-based data. And so, go back, you guys. They keep moving it for me. Go back. Back. One more, right there. So when we're joining point structural data with interval-based data, we've got like geochemistry, we've got our quality control for filtering, lithology logs. You can join it with all kinds of interval-based data types. And really this gives us the ability to design a query and interrogate this database. You may have 150 holes with 5,000 data points, and we need to rapidly ask that database a question and get an answer for 3D modeling. So, go ahead.
How much of the data is corrupted if the core tube isn't oriented correctly?
Well, you can't just answer that question like how much. It's basically how your process is trained. And if we get in there and train people at the beginning, and it depends on the rock conditions as well, right? So sometimes, like if you're in Canada, there's stick rock everywhere. I work in Alaska and Nevada and places like Mexico and Argentina where the rock conditions are very bad. And so we've got to make a little more effort to get good orientation. But we can do it because we're used to training in those kinds of conditions if we can control the tube. And then that's why in that last slide we have that filtering system where we're creating an attribute for each structural data point so we can weed out the bad data and keep it out of the model. Okay, did that answer? Yeah, yeah, right. I probably went too far. But the next stage is taking that data and plotting it on stereo nets. I don't want to get too deep into this stuff here, but what we like is IOGAS software. Really helps us have the ability to make these thematic stereo nets where we can take data and we can visualize it using different sizes and shapes and colors. And basically these are all like, this is a 4-parameter query for a bunch of veins from a bunch of different holes that have been drilled. And we can see that right away that, the color is representing gold mineralization. So these are veins existing within high-grade gold intervals. And we can see there's a population here that's dipping very steep to the north-northwest, and maybe a second-order population of veins that's dipping moderate to the east-northeast. And if we could see this in real time as we're drilling, it's very valuable for exploration. But really, we can look at these all day, these stereo nets. But the next question is, how is this distributed in 3D space? Are these points just scattered all over the drill program, or are they forming discrete zones that we can model and target? And that's really where we're going with this. So there's a few tools out there that we've talked about, that we like this ecosystem where, Index has oriented core tools, survey tools, IQ logger for collecting structural measurements, all talking to get to each other within this index hub. linking into 3D. But what we prefer is to have a little bit of constraint where we're able to take that data and boil it down before we go into 3D. Because if you just, use these systems, you can now get to the point where you can measure your structures in core and get that structure to pop up in 3D in real time as you're measuring it. But we're saying, hey, let's take the data through some steps and clean it up, boil it down. And this is an example of that. This here is a stereo net that's for a porphyry system in Canada. It's a stockwork system of veins, and it's very organized. There's two sets of veins that are dipping at each other. And if you take that population and throw it into 3D, it turns into this big cluster of plates on drill strings, which is very confusing for a geologist to understand. And so the reason why we use the word constrain over and over again is because we need to reveal the order that exists inside of this chaos. Go back. You guys go back. So basically, if we just look at one of those conjugate sets at a time, then you can see the order that exists within that chaos, where you've got intersecting vein populations, and there's copper grade bars going crazy at those intersections. And it happens once, it happens twice, and that's kind of how we're able to take a very complex data set and pull some order out of it, just through querying, filtering, and boiling the data down. So I'm going to go over a little bit of it in Leapfrog. What we've got going on here is like the next steps of taking the data into 3D. And what we like to do is basically use the StereoNet module that's in that software, and we can make a category selection and just name structures what they're doing. Like basically that polygon on there is just saying that's the northwest dipping set of faults, and we can actually rotate the scene view in 3D and make a decision to make a mesh. And in this system, you can see that these meshes here are basically have copper grade shells following the footwall boundary of these faults. And in that system, that was a very valuable targeting tool regionally for that client, and it was because they were able to turn off most of the data and just look at one thing at a time in 3D, and that's really what we're going for here. So the end result with this workflow is, if we're able to get a good accurate signal from the rocks and just listen to that and have the ability to model it, there's a lot of value in that. We're basically getting empirical data that's actually showing us the geometry of these systems that we're targeting. And, that's why I got into this stuff, is because I just wanted to get the signal out of the rocks and just hear what they have to say, and then know if I could trust that data and basically use it for targeting. And so we're really trying to also, with the joining of the point data with interval-based data, we're revealing relationships between structure and everything that it controls, like alteration, geochemistry, things like that. Go back, you guys. Keep flipping it on me. It's really about mineralization vectoring, improving resource modeling, and also geotechnical engineering. And so if we get the opportunity to get on site, OTS, we start working with the drillers first. We get them to thoroughly understand how to use the tools. It usually takes a quarter of a shift. It's not much time. We get in, we get out. We get them trained. We talk about mitigating errors, and also we have a block marking process so that any errors that they observe at the rig can get transferred into whoever's logging the orientation. And then we work with the geotechs and geologists next in the core shack. Go back. We work with geos and geotechs. We work with implementing a quality control system for the logging. We get them to understand what to do with the data, how to join it, how to basically filter, query, and basically get 3D meshes built and have some constraint to their 3D modeling. And so in summary, really what we're trying to get geologists to do is treat the core like an outcrop and make a map with structure involved. If you, like I said before, if you send out mappers on a mapping program, there's no way you're going to tell them to ignore structures, so we don't think it should happen with core either. Develop a practical workflow. I'm an old project manager on many projects. I understand the limitations of time and personnel. It's a real problem. We don't want to bog people down. But I think if you decide to do this, focus on the quality control first to give yourself a chance to get value out of the data. Don't load garbage into your 3D models. That's the thing. That's why we work on this quality control. More data is not always better, and I think other than that, develop queries. We want you to have the ability to interrogate a complex database and get answers quickly. And the biggest point that I want to make here is don't just collect data, actually do something with it. That's our biggest fear, is just seeing data go into a database and not get used. Anyways, thank you for your time. I appreciate it.